Everyone, in this video, we're going to look at example 3 in section 6.4. All right, so let's read the question. So in example 3, we're given a cylindrical tank having a radius of 0.5 meters and a height of 2 meters. And we're told that it's half full of kerosene, which has a density of 800 kilograms per meter cubed. We need to find the work needed to pump the kerosene over the edge of the tank. Okay, so to get started, let's go ahead and just decorate this tank a little bit with the information that we're given. Okay, so we're given that the radius of the tank is 2 meters. I'm going to draw that in. So we have 2 meter radius here. Oops, not 2, 0.5. 0.5 meters. And that the height of the tank is 2 meters. So we're at 2 meters tall. Okay, and we're told it's half full of kerosene. So we could think of this shaded area as like the top of all of the liquid here. Okay, so what are we asked to do? Well, we're asked to find the work needed to pump the kerosene over the top of the tank. So let's just review how we would compute work. So work is equal to force times distance. And in our problems, when we're dealing with examples where we're assuming we're on the surface of Earth, force is going to be weight. So the force that we use is the force due to gravity on a mass. So that for us will be weight. So we need weight times distance. Okay, so that's just a little reminder about how to compute work to move an object. But in our problem in particular, our kerosene is down here at the bottom of our tank. And we should think of the kerosene being pumped to the top of the tank. That's our goal here, find the work needed to pump the kerosene over the top of the edge. We should think of that pump as sucking up kerosene just at the top of wherever it is. So we can think of that pump as maybe resting on the surface and sucking up kerosene. And so then as our kerosene level goes down, so as we decrease our kerosene, that pump is going to then go down as well. So now maybe we're here, so the pump's here. And so why we want to think of the problem like that is because various levels of kerosene, so maybe here's a little slice or level of kerosene, is going to have to travel a different amount or a different length to get to the top of the tank. And this way too, we don't, if we just kind of sucked up from the bottom, then this layer of kerosene would have to go all the way down and then up. So just to kind of simplify our problem, in cases like this where we're pumping volume, or maybe we're pumping, I don't know, animal feed out of a bucket, let's assume that we are moving these layers of our substance just straight up. Okay, so that also foreshadows the method that we're going to use to compute the total work needed to move this kerosene to the top of the tank. And that method will be is that we're going to slice up our kerosene. It's kind of weird to think of slicing up our liquid. We can think of it as slicing up our kerosene. All right, slice here. And then determining the work needed to move one slice, and then adding up all of our slices together, or all of the work needed to move the slices using an integral. Okay, so let's go ahead and carry that idea out. So in order to compute, so as we did in the previous example, our kind of goal here is to compute work needed to move, I'll say pump, needed to pump a slice to the top. Okay, so again, that work, we need to compute force times distance. So let's go ahead and start with computing the force. So force on slice. So that is going to be equal to the weight of a slice. So weight is equal to mass times the acceleration due to gravity. So in order to compute that weight of a slice, we need to compute first the mass of the slice. So for a given slice here, we can determine its volume, and we can determine its density because we're given that value in the problem. And then from there, we're just going to multiply by that acceleration due to gravity. Let me pause here and I'll rewrite this so we don't get at the end of the page. Okay, so here I've rewritten weight of a slice is going to be volume times density, because that'll give us the mass, times that acceleration of gravity. Oops, and let's just go ahead and check where our units are at. So volume, we're given all of our dimensions of the tank, and so therefore the slice in terms of meters. So our volume would be meters cubed. The density is given to us in kilograms per meter cubed. So those two would cancel out. Meters cubed would cancel. And then the acceleration due to gravity is a meters per second squared. So we see here then the final units would be kilograms per meter squared, which are newtons, which is what we want. Okay, so let's go ahead and fill in this information with what we know. Okay, so let's first determine the volume of a slice. So what kind of shape does this slice have? We see it's a little slice out of a cylinder, so it looks like a disc or like a very short cylinder. So to compute the volume there, we can use these dimensions given to us for the tank. So the disc has a radius of 0.5 meters. So then the surface area of that disc would be pi times r, which is 0.5 squared. Would be the area, so again, surface area of just that top part. Then we need to multiply by the height of that disc. So for us, we could call that variable, or this change, y. So a little bit of change there would be dy. Okay, now the density, we're given 810 kilograms per meter cubed, so 810. And then finally, we have our acceleration due to gravity as 9.8. Okay, so now let's just gather what we have together to kind of simplify things. We'll put a 0 in front there, so it's really clear that we're at 0.5. Okay, so we have some numbers that we can multiply together. This is combining our like terms, so to speak. So we multiply 1/2 squared times 810 times 9.8. We are going to get 1,984.5. So go ahead and consult your calculator to make sure that number is correct. And then we have a remaining a pi and a dy. And as we checked with units, the units we should have here are newtons. Okay, so again, our goal is to find the work needed to pump a slice up. We computed the weight, which is the force needed to pump the slice up. So now we just need to compute the distance traveled by the slice. So we'll write that out, distance traveled by slice. Well, if we measure from the top of the tank down to where our slice is, we can call that y. So the distance traveled by the slice would be y meters. Okay, so what does that mean? That means that for total work to move a slice to the top is equal to 1,984.5 pi y dy. Okay, and so this is just to move a slice, but we figured out the work needed to do that. And just so we check what our units are, So our distance traveled is meters. Our force is newtons. So this would be Newton meters or joules, which is an appropriate measure of work. Okay, so now we're going to put our calculus tools to use and determine the total work needed to move all of the slices up. So therefore, the total work needed to pump the kerosene to the top of the tank is given by computing an integral where we add up the amount of work to move each slice. So that would be the integral of 1984.5 pi y dy. And now we need to consider the bounds of our integral. So what is y? What are the range of y here? Well, we can consider the closest kerosene to the top. That closest slice occurs halfway down the tank. So halfway down the tank is going to be at 1. And then what about the farthest a slice has to move? Well, the farthest a slice has to move would be a slice at the bottom, and it has to move a total of 2 meters. So then the bounds of our integration are going to go from 1 to 2. So we're going to put here 1 to 2. So now we can just carry out this integral. So this 1984.5 pi is just a constant, so we can factor out, and we just need our antiderivative of y. So that's going to be 1984.5 pi times y squared over 2, evaluated at 1 and 2. All right, so let's go ahead and plug in those bounds. So we're going to get 1984.5 pi times 2 squared, which is 4 over 2, minus 1 squared, which is 1 over 2. All right, so at this point, we can go ahead and consult our calculator, carry out all of this multiplication to compute what our final solutions should be. And you can check me and carry this out for yourself, but I'm getting about 9,352. And so again, we're adding up all of these little bits of work, which are joules for each time. So in total, we get joules as our final unit. All right, so there is our solution for the total amount of work needed to move this tank that's half full of kerosene, needed to move this kerosene to the top of the tank. All right, thanks so much for watching, everyone.